So let's look at another example. So here we have a machine that produces acceptable products 70% of the time. A team uses the machine to produce 2 items. We want to find the probability that none of the items is acceptable, exactly one of the items is acceptable, and both items are acceptable. And then we assume independence. Now let me go ahead and first denote. So let A denote an acceptable product, and then let D denote a defective product. Okay. So then I'm not going to go through the details. You should be able to verify that this is indeed a binomial experiment. And for that reason, if success is defined as getting an acceptable product, right, then the variable x, which denotes the number of successes in other words, the number of acceptable products from we get in this experiment, right, is so x is a binomial random variable. Okay. So now what do we know from this problem? So we know that this is a binomial experiment with n equals 2 trials. The probability of success is 70%, which is equal to 0.7. And so we want to find the probability that x is 0, the probability that x is 1, and then the probability that x is 2. Okay. Now, at this point, there are 2 ways to proceed. You can either punch these numbers into a calculator using the binomial probability function formula, or we can use the binomial table. I'm going to use the table to show you how we can find probability with the table, but if you want to use a formula, that's fine with me too. So we want to go to the table. Go to the part of the table where n is equal to 2. So we are right about here, right? We want to look under column 0.7, which is this column, and so these are the values that we want. So for 0, the probability that x is 0 is 0.09. The probability that x is 1 is 0.42, and then the probability that x is 2 is 0.49. So we can go back and answer the question. So this is 0.09, this is 0.42, and then this is 0.49. Now let me go a step further. Let me put this information into a table. So I have a table with x, 0, 1, and 2, right? let me have a column called composition. So when we have when x is equal to 0, that means that we have no acceptable products, and that means we have two defective products, right? So here we have two D's. When x is equal to 1, we have 1A and 1D. And then when x is equal to 2, we have 2A's. And then let's fill in the probability. So this is 0.09, 0.42, and then 0.49. So nothing fancy here. I just literally put the information from the line above into a table. So now let's think about the following situation. What if I define success as getting a defective product? So what if success is equal to getting a defective product? Okay. Now you may be wondering why. This is really counterintuitive, right? Why is success getting a defective product? And my response to that is, why not? Okay, so think of the following example. Suppose you flip a coin, right? When you flip a coin, you have two possible outcomes. You either get a head or you get a tail, right? So when you flip a coin, you can define success as either getting a head or getting a tail, right? There's not a rule that says you have to define success one way or the other, right? So success can be either head or tail, right? There's not a rule that says you have to be there's not a rule that says success has to be a head or success has to be a tail, right? So same thing with our problem here, right? So if I define success as getting a defective product, then the variable I'm gonna call it the variable y, which denotes the number of successes i.e. the number of defective products is also a binomial variable. Okay. So now what do we know? We know that this is an experiment with two trials, so n is equal to 2, but what is the probability of success? Remember that the machine produces acceptable products 70% of the time, and so that means that it produces defective products 30% of the time, right? So the probability of success here is going to be 1 minus 0.7, which is going to be 0.3. And so we're interested in the probability that y is equal to 0, the probability that y is equal to 1, and then the probability that y is equal to 2. Okay. Let me put this on the in the table. Right, so y here I have 0, 1, and 2. Let me have the composition column. Now when I have 0 defective products, that means that I have 2 acceptable products, right? So here we have 2 A's. If I have 1 defective product, that means I have 1 D and 1 A. And then when I have 2 defective products, then I have 2 D's, right? So now to find probabilities, let's use the table again. So when you go to the table, you still want to look at the part of the table where n is equal to 2. But now you want to look at column 0.3, right? Because the probability of success now is 0.3. So these are the values of interest: 0.49, 0.42, and 0.09. So this is 0.49, this is 0.42, and this is 0.09. Okay, so I'm gonna So for this table, we have success being getting a defective product. Okay. And let me bring the previous table over here. So I have x, 0, 1, and 2. I have composition, and then probability, right? So I have 2 D's, 1 A, and 1 D, and then 2 A's, right? And my probabilities from before was 0.09, 0.42, and then 0.49. 0.49. Okay. And then over here I have success as getting an acceptable product. Okay. So in a sense, right, these two tables are just mirror images of one another, right? And so the idea here is that when you construct the probability distribution of a binomial random variable, it is very important that you pay close attention to how a success is defined, right? So need to pay close attention to how a success is defined. Once you define what a success is, make sure you stick to it and use the appropriate probability of success. So in this video, we did an example where we apply the table to compute probabilities for a binomial random variable.